So our guest and lecturer today is Professor Peter Goldreich. Professor Goldreich has made a profound and lasting contribution to planetary sciences and astrophysics. Among others are understanding the rotation of planets, the dynamics of planetary rings, pulsars, the spiral arms of galaxies, oscillations of the sun and white dwarfs, and turbulence in magnetized fluid and planet formation, and more. Professor Goldreich received his PhD from Cornell University in 1963. He then went to a postdoc position in Cambridge for 2 years, came back to UCLA for a while, and then in 1966 moved to Caltech, to California Institute of Technology. He was there the Dubridge Professor of Astrophysics and Planetary, became a Professor Emeritus in 2003, and moved to the Institute of Advanced Studies in Princeton. He was there a professor for some 6 years and became a Professor Emeritus in 2009. Professor Goldreich received many prizes and awards for his scientific achievements, and among others he was elected to the National Academy of Science in 1972, a year later to the American Academy of Arts and Sciences. He received the Chapman Medal from the Royal Astronomical Society in 1985, the Dig Brouwer Award from the American Astronomical Society in 1986. He received the Kuiper Prize in 1992, the Gold Medal of the Royal Astronomy Society in 1993, and the National Medal of Science in 1995. He was then elected as the foreign member of the Royal Society in 2004. He received the Grand Médaille of the Académie des Sciences in France in 2006 and the Shaw Prize in 2007. So we are very pleased that he agreed to come to talk to us. Professor Goldreich is visiting Israel mainly because he was invited by the Israeli Academy of Science. He's giving a talk there, and when I asked him, I thought it's a good opportunity to have talk to us too. And but different than in other cases where here are giving professional talks on science work, Professor Goldreich decided to talk to us about physics of everyday life. And I thought it's a nice change and a welcoming change from our usual way of doing it. So I was very pleased that he agreed. Thank you very much, Peter.
Okay, so first I'm going to talk about ordinary humans. Ordinary humans eat around 2,000 kilocalories of food per day. And that's enough to give you the power for everything you do. And it's equivalent to 100 watts. Then you might wonder where all this power goes. And you see from what I've written up here, about 20% of it goes in your brain, but your brain is only a very small fraction of your weight, maybe 1 to 2 kilograms of maybe 70 kilogram weight, and 5% in your heart. So this shows that really the brain is the center of us. And you might ask also, I was asked once and didn't know the answer, how much of the power expended by other animals goes to the brain as opposed to other places? Well, I now know the answer. For anthropoid apes, it's more like 8 to 10%. For dogs and cats and just about everything else, all other mammals, it's 4 to 5%. So you see that we developed, actually fairly recently, to focus our energy where it really mattered in our brains. And that makes up for our rather weak physiques. Okay, so now I'd like to say a few words about walking. If I can find my, whoops, here it is. So here's what happened.
No,
Oh. Okay. I didn't touch the metal, so you don't have to pay my widow. Okay, so this is a pendulum. I assume everybody in the audience has had some experience with a pendulum, and you know that the frequency of oscillation, of small oscillations of a pendulum, is just proportional to the inverse square root of the length. Frequency just goes as the square root of little g divided by L. And you also probably know that you all have natural walking speeds. You might wonder what the natural walking speed is due to. Well, it's due to the fact that depending on how tall you are, pretty much only on how tall you are, you tend to walk best or feel most comfortable walking when your leg swings at your natural pendulum speed or angular speed or frequency. And then your velocity, the velocity of walking is given just by more or less the length of your leg times that frequency, so it goes as the square root of GL to the 1/2. And that's why, for example, if you have a little kid walking along with you and you're walking at your normal speed, the little kid is going to have to run. The distinction between running and walking is in walking, you always have 2 feet on the ground, or 1 foot on the ground, and in running, part of the time you have no feet on the ground. So that determines what's a natural walking speed. Okay, I want to just do one more sort of normal exercise. This is climbing. If you have an energy E that you can expend in physical work, I'll talk about how much you have to eat in order to do that, then you can climb a height, if you're really efficient, using that physical or mechanical energy, a height which is the energy you have divided by your mass times the acceleration of gravity. And actually, 1 meal is enough to get you quite high. So for example, with one meal you can get up a few kilometers in height. But of course, in general, you need to eat many meals to get up that high. And that's one of the reasons is because your muscle efficiency is only about 25%. So of the food that you eat, only about 25% can go into sustained physical work. That's about as good as an automobile engine can do as well. In fact, it's as good as about all normal engines that we deal with can do. It's not as good as modern airplane can do, and I'll discuss that a little when I discuss flying at the end of this lecture. So now I wonder how many people have, for example, ever vertically ascended more than 1 kilometer in a day? Yeah, okay, there are a few old guys here who claim to do it. How about 2? 3? It's really not that hard. I've done 3.5 without a trail. From the floor of Death Valley in California to the top of Telescope Peak. 11 hours. And a meal every hour. So it's quite possible to do these things, but they take a lot of food. Okay, so now I want to talk a little bit about the use of energy in doing exercise. So that's shown here. When you're walking, first when you're standing, you're burning this is metabolic power. So this is the total power that comes out of the food that you eat. You're pretty good, unfortunately, in using all the calories that you eat. So just standing still or even sitting, you use about 100 watts And then when you start walking, the power you need goes up. And you see that the power goes up steadily, but there's a break in the curve here between walking and running. Because above a couple of meters per second, maybe 3 meters per second, it's more efficient to run, at least if you're young and reasonably fit, than it is to walk. And you can see that on this graph here. The energy cost in joules per meter now of distance traveled is a function of the speed in meters per second. And you see this curve has a very nice U shape for walking, and there's a sweet spot here at a bit less than 2 meters per second, but after that it's more efficient to run. And in fact, that's why in races the best race walkers can't go quite as far in a given amount of time as the best runners. The best race walking, I think, is about a 5-minute mile, and runners now go well below 4 minutes. Okay, so now we're going to leave the realm of ordinary people.
By the way, what is the maximum?
How much power?
Yeah.
Oh, 200, 250 watts sustained power is about what a human can do. By the way, all this stuff is pretty well measured through masks, which measure how much of the oxygen you take in, you turn into CO2. It's not only measured for humans, it's measured even for birds. So these things are fairly well known. Of course, they depend a bit on body size, and they're a little bit different for men and women, but not very much different. Okay, so I want to talk about sports a bit, and about how you can understand at least some simple sports in terms of physical terms. Now, these are specially chosen sports. For example, I won't be doing running. Running is quite difficult because the loss of energy, of kinetic energy when you run is complicated. Depends upon how much is returned by your Achilles tendon, what sort of track you're going on, what sort of shoe you wear. But there are a few that are particularly simple. And one is pole vaulting. Does everybody know what pole vaulting is? You know, you have this big pole, and the people who do it well are basically sprinters with strong upper bodies. And they go running down the track. They stick the pole into something that's called a cup. The pole bends. Their kinetic energy is converted into potential energy stored in the pole, and then the pole propels them up, and then they do their best to keep their center of mass below the height of a bar. They slither over the bar, and they fall in, if they're lucky, they fall in a foam pit. And the best ones can do just about 6 meters. You might wonder, where does the 6 meters come from? Well, it comes from the following 2 considerations. First, they tend to be taller than I am, and so their center of mass to begin with is already 1 meter off the ground. And then, since they're pretty good sprinters, they sprint at about 10 meters per second. That used to be close to the world record. It isn't anymore. From various improvements, both in equipment and also in body type, the record's gotten somewhat better. But anyway, if you convert 10 meters per second running speed into potential energy, then you should be able to lift your center of mass an amount v squared here. You get potential energy v squared over 2g, and if you set that equal to mg times h, it's a very easy calculation to see that that gives you 5 meters. So you add that 5 meters to the 1 meter that you already have. There's a little bit of a loss in the pole, but you make up for that by pushing with your arms at the last little bit, and also keeping your center of mass slightly below the top of the bar, and you get 6 meters. Now, the world record has been essentially 6 meters for a long time. I think Sergei Bubka set this record 20 years ago, and it's just been broken. But it's been broken by some tiny little amount. And to show you how it works, I have I hope. This is the Olympic record, or was the Olympic record. So see what he does. It's from YouTube. Oh, I should have put it on an audio, I guess, huh? Is there a way to get an audio that can be projected to? Okay, so now you all know what pole vaulting is, but I can tell you it's not easy to do. Now I want to talk about another Olympic sport. Oh, by the way, I prepared this lecture for donors at the Institute for Advanced Study. They were more interested in the last part, which had to do with weight loss. But I prepared it quite a while ago, so I can't vouch for all of these world records. Some of them may be a little out of date. But the improvement in drug testing has made the records stand quite well over the last decade or so. So they're probably not too far off. So this concerns weightlifting, something which I never did. And there are two main events in weightlifting. There's the snatch. And in the snatch, the competitor bends down, he goes, ooh! And that gives this set of records. These are the weight classes in kilograms. And this is the world record weights as of, I don't know, a decade ago. And then there's the jerk. And you see the records are higher for the jerk. And the reason is that for the jerk, there are two motions. First you bend down, you go like this. Whoops, I'm going to pull it out again. And then you lower your weight and you get it up and you come up. So it's a two motion. It's a little bit easier. And you'll see that the second motion is squatting under the weight. The weight stays in the same place and the body squats down. There's a question of how you tell. And we had this very good weightlifter. I think his name was Tommy Kono. When I was a kid. And he had won in several weight classes. So I tried this procedure out on him and his contemporaries. And it worked very well. He stood out after the scaling. So the question is, how would you scale the weight that somebody can lift as a function of body size? Well, it makes some sense that you would scale by the 2/3 power of the body weight, because the muscle cross-section is probably what's really important. And that more or less goes as the 2/3 other dimensions, 2/3 volume, and our density is more or less out of water. And so this second set of columns, this column here shows the snatch scaled by the 2/3 power of body size, and then the jerk scaled by the 2/3 power of body size. And look how almost constant these world records are when scaled this way. And also notice, I'm not quite sure what the answer is here, but notice that the middle weights are slightly better than those at the low and the high end. Forget about the unlimited, because they're just big fat guys. They can weigh anything. But on all the others, it's pretty good. And you might ask, why are the middle weights better? Does anybody have an idea? Why would the middle weights be better? Why not be tipped one way or the other? My guess, it's only a guess, is that there's just more people in the middle. Competition is tougher, and so they're a little better. But I don't know whether that's really true. It's just a guess. Okay, now we're going to watch some of these events. At least I hope we're going to watch it. Yeah. This guy's 19 years old. He's a Turk. And you'll see what I mean about the steroids at the end. Sorry it's such a lousy reproduction, but... So this is the snatch. Okay. It's probably not very good in physics.
But you could serve here. Very strong.
Okay. So that's the snatch. Now you'll see the clean and jerk. Now, see if you can tell whether the bar hits the chin of the competitor at the end of the lift. I still can't tell for sure. Watch him go down. See? I think he just saw it coming up and pulled his head back, but I'm not sure. Okay. Okay, now unfortunately I don't have sound on this next one. Can you hear any of this in the back, any of what's coming out of my computer? Okay. This one some of you may have seen. It's from the old drug Olympics. Has anybody seen this one from the old drug Olympics? No. Unfortunately, I don't have a big Russian. The one time I gave it, I had this very big Russian. He's a professor, but I had him come up and I showed this. And he almost fell down laughing after.
Dennis, getting ready to lift now is Sergei Akhmudov of the Soviet Union. His trainers told me that he's taken anabolic steroids, Novocaine, NyQuil, Darvon, and some sort of fish paralyzer. Also, I believe he's had several cocktails within the last hour or so. All of this, of course, is perfectly legal at the All-Drug Olympics. In fact, it's encouraged. Akhmudov is getting set now. He's going for a clean and jerk of over 1,500 pounds, which would triple the existing world record. That's an awful lot of weight, Dennis, and here he goes. You know, you hate to see something like this happen, Dennis. He probably doesn't have that much pain right now, but I think tomorrow he's really going to feel that, Dennis. Back to you.
All right. Okay. So much for weightlifting and sports. I'm going to.
Peter, what's the explanation for the power of 2/3?
It's just the square root. It's just the area of the muscle compared to the volume of the body, assuming that you have optimized. I mean, these people, of course, all have special bodies that they've developed and also probably were endowed with to some extent. And so you just scale them, and the hypothesis is that it's the muscle cross-section that determines what you can lift. Of course, these are optimized individuals, and that's the 2/3 power of the volume. And you see it works very well. There are many others, by the way, that work very well. I'm just showing you a small sample. Maybe I'll go back quickly because I left one out. I left this one out. This is cycling versus swimming. These are also reasonably easy to understand because there's only one thing determining how fast somebody can swim other than their own power and stroking ability, and that's drag. So when you're riding a bike, the main work you're doing is against wind resistance, at least if you're a top-level rider. And when you're swimming, the main work you're doing is against water resistance. Now, in both cases, the Reynolds number is so high, don't worry if you don't know what Reynolds number is, that the drag is due to turbulence in the fluid that you're moving through. But there's a big difference between bicycling and swimming because the air density is almost exactly 1,000th at sea level of water density. So the swimmers are going through a much denser medium. Now in turbulent drag, the drag force is proportional to the cross-sectional area, some coefficient, which the competitors tried to make as small as possible, called the drag coefficient. It's just some number. We can think of it as a half or so, and then we can argue about what the cross-sectional area is in swimming and cycling, and the velocity squared, and the density of the medium. The power that's expended is proportional to the force times the velocity of moving through that medium. So the power is expended, it goes like v cubed. So you have the force going like v squared, the power going like force times velocity, and therefore you would expect that the maximum sustained velocity that a really good swimmer could maintain would be lower than that a cyclist can sustain by the cube root of 10 to the minus 3, or 1/10. And that's just about right. So I have here where I can see it, but you can't, what the world records are. The world record in long races, in cycling is about 50 kilometers, and swimming about 5 kilometers. So that's a pretty good scaling. So again, it shows you that this hypothesis is reasonable. Of course, the fact that there's a cube root coming in softens any errors that would be made because the cross-sections aren't quite the same when you're crouched over a bike or when you're swimming. And also, I really should have be a little bit careful because when you're swimming, there's also some wave drag if you're swimming on top of the water as opposed to under the water. But compared to the turbulent drag, it's small. Okay, so that's cycling versus swimming. So let's get on to cooking. Okay, so now I'm going to tell you everything I know about cooking in about 2 minutes. Okay, so first, what about the heat storage in pretty much any material, at least at room temperature? Heat stored in lattice vibrations, in the vibrations of the atoms, and these are, you can think of as organized into modes of different wavelengths, but most of the modes are very short ones. They have wavelengths that are just a couple of spacing of the atoms. And the atom spacing in almost everything that we eat is pretty much the same because almost everything that we eat, at least if we put it in water or so on, it's going to have density not that different from water. And then the heat diffuses because these lattice vibrations, they're waves, they don't propagate very far, not the short wavelength ones. Of course, the big ones propagate a long distance, the long wavelength ones, and this is a subject for waves and solids and so on. But the short oscillations only propagate a number of lattice spacings themselves. Mostly they scatter off various defects, or they scatter off each other. And so that means that the diffusion of heat in essentially all dielectric media, as opposed to metals, is more or less the same. It's a few angstroms for the lattice spacing, and then you multiply by a few lattice spacings, so maybe it's 10 angstroms. And the speed of propagation in these solids is a few kilometers per second. If you multiply those two together and divide by 3, if you really want to try to do a good job, you get a diffusivity of about 0.01 centimeters squared per second. So the time it takes heat to diffuse from the outside of your roast to the inside of the roast, if you have it in an oven, an ordinary conventional oven, as opposed to a microwave, where you can heat it directly towards the inside, that's just given by the length squared divided by this diffusivity. And this works essentially for everything. It works for the time scale it takes for a big body, like a small moon to cool by conduction, for the time it takes for heat to come in from the surface of a roast into the center to denature the proteins, which is what we mean by cooking. And so this gives you very good scaling. You can scale everything from a boiled egg to cooking a whole pig. And you do pretty well. It would help to have a meat thermometer, but it's not essential. So anyway, that's cooking. Cooking time goes like mass to the 2/3. And I looked in a cooking book and for turkeys of different size, and this works pretty well. So that's all you really have to remember. That's cooking. That's why I don't do it. It's a solved problem. Okay. Now I'm going to talk about flying. Okay? Flying's actually fairly complicated, but it can be reduced to something fairly simple. So, what happens when something flies? Well, almost anything can fly if you attach a strong enough engine to it. And for a while, that's what we did in the US. We had planes that were shaped like boxes because they were cheap to build, and we just put a big engine on them, and we pulled them through the air, and they flew fine. But of course, now fuel is expensive, and so we want to get every possible drop of fuel to its maximum in propelling and lifting a plane, so the shapes are a lot sleeker. But the basic idea is as follows. You have something like this. It moves through the air. It presents some cross-section to the air that gives it drag. You have to move it by pulling it. Then you tip the wing up a bit like this. And you have air come striking it this way. There's a certain amount of lift. You have to be careful not to tip the wing too much or you'll stall. And that's about all there is to flying. Except that it's a big business, and to optimize it is not easy. But you can scale flying very well. And it turns out that the efficiency of flying has been improved by both man and also by birds and insects and so on, so that there's a wonderful scaling between everything from the smallest little insect to the biggest commercial airplane. As long as you stay under the speed of sound. Once you get above the speed of sound, these scalings change. And they're determined by these two equations. The first one gives the lift that you can generate. The lift that you can generate is some dimensionless coefficient called the coefficient of lift, capital C sub L. Then there's some cross-sectional area that the plane presents. If things are done well, most of that's in the wing, not too much in the fuselage. There's the density, in this case the density of air. there's the velocity squared, and then just by convention, you divide by 2. This is the same thing that I discussed, really the same sorts of scaling I discussed for the bicycles and the swimmers. And then there's a drag, which depends upon all the same things, but with a different coefficient. And of course, the good thing is the lift, and the bad thing is the drag. So the sophistication in flight is to maximize the lift for a given amount of drag, and that's called the finesse. On the other hand, if you want to get somewhere fast, then you sometimes sacrifice a bit of that ratio. Okay, so how do we get the speed? Well, in order to get the speed, the lift has to be able to balance the weight. So we can set that first expression for the lift equal to the mass times the gravity, and we can solve then for V. Now, how did I do that? Well, I assumed that for optimal flying, there's some relation between this A and M, and that both of them depend upon some overall dimension of whatever the thing is. And so if you take that and you solve for V squared here, you have V squared proportional to M over A, and A is M to the 2/3. It's again just like the weightlifting scaling. And then if you solve for V, you have to take the square root. You get V going like M to the 1/6 power. Okay, so now I'll show you the great flying diagram. It's a little hard to see from back there, but you'll get the idea. Okay, so this diagram here, this line that runs through it is this M to the 1/6 power. This is velocity, or the log, it's a log scale. For velocity on the abscissa, on the x-axis, velocity measured in meters per second, going from 1 meter per second here to 100 meters per second, 200 meters per second right at the end. And here's mass, going from 10 to the minus 5 grams all the way up. Oh, excuse me, it's 10 to the 5 newtons, yeah. 10 to the 5 minus 5 newtons all the way up to 10 to the plus 6 newtons, almost 10 to the 7 newtons. So at the bottom here we have a midge, a housefly, scorpion fly, dragonfly, various butterflies, and up at the top we have airplanes. And this diagram was made before the big and somewhat unsuccessful Airbus. So the biggest airplane here is the 747. And all these points just represent these different beasts and airplanes and so on. And you see it's a pretty good 1/6 power. This is not my diagram. This came from a wonderful book called The Simple Science of Flight by Technion-Israel. I just think that's really amazing. Okay, I go back one more time. So now I'm going to talk a little bit about the range. When I first started teaching order of magnitude physics, birds could fly as far as airplanes. So migratory birds could fly across oceans. They took a lot longer because this speed was related to mass, and their mass was a lot smaller than the mass of airplanes. But at that time, when the birds took off, their weight was 50% higher than when they landed. They would eat and eat and eat. They'd build up these big chests, and they would fly sometimes for days. The airplanes, when they took off, the ones that went across oceans, they would have half their weight in fuel. And the bird muscles were about as efficient as our muscles. as efficient as the airplane engines, 25% mechanical power compared to metabolic power. So that was the story then. But now airplane engines are almost 50% efficient. And so airplanes can go quite a bit farther than birds. Like the one that brought me from California from Los Angeles to Tel Aviv. Went almost 7,500 miles on one drink. Okay, so now how does that work? Well, if you ask what is the range, well, the range that you can get for a flying machine is the mechanical energy that the fuel can provide divided by the drag force. So the drag force times the range is equal to the mechanical energy, and that gives this ratio. This ratio of the lift coefficient to the drag coefficient, sometimes called the glide ratio or the finesse of the plane, and then just the ratio of the energy divided by mg. Now, this ratio at 25% efficiency is enough to get you about, I think it's 750 kilometers up in the air. So if you take an amount of fuel that's equal to half the weight, and you take into account that the fuel is worth something like, I think it's about 10 joules, no, 10 cal, no. I'm sort of forgetting now. It's about the same as eating fat, but I forget exactly what the number is. Then you get about 750 kilometers. But airplanes can go about almost 15,000 kilometers. And the reason they can do that is that their energy efficiency now is about 50%. So that doubles this from 750 to 15, yeah, it almost doubles this. And then a 747 has a ratio of lift to drag, which is about 15. So that gets you the rest of the way. I think this turns out to be about 500 kilometers with the current engines, and then you get about a factor of 15 here. We're not going to squeeze much more out of that. Okay. Okay, I want to talk a little bit about weather. This is my, well, actually I forgot one other thing I was going to talk about. Maybe I'll go back and just, yeah, I was going to talk about sweating. When you do sustained exercise, as I mentioned, something like 3/4 of the energy that you consume just goes into waste heat, and you have to get rid of that. If you ask how much heat do you dissipate or have to get rid of, for example, if you exercise for an hour, cycling or running or even swimming, although it's not so much of a problem in swimming because you have the water next to you, then you have to get rid of something like, I think it's about 750 watts. And you have to, yeah, well, excuse me. Let me see if I can recover this. Maximum sustained mechanical power is 250 watts. Waste heat is 750 watts, yeah. So you have to get rid of, so the 750 watts would be sufficient to heat a 70 kilogram human up by about 9.6 degrees centigrade in an hour, and that would be death. And there's no way you can get rid of this by radiation or by conduction. The only way you can get rid of it is by sweating. And so you have to sweat enough to get rid of all of this energy. And if you work out with the latent heat of vaporization of water, then you have to sweat something like 1 to 2 kilograms of water in an hour of really hard, sustained exercise. Of course, this is not exercise that most of us ever come close to accomplishing. This is really sort of top level. Okay.
This is, by the way, the maximum rate of intake of water for human beings, about a liter per hour.
A liter per hour? Okay, so last thing I want to talk about is weather. So I'm gonna talk about first. Oh, maybe I'll do that before I do this one. First, I want to talk about how much it rains. So something like half of all the sunlight that falls on Earth is used in evaporation. The oceans cover 2/3 of the area of the Earth, and most of the energy falls in the lower latitude regions. And that then tells you, given the latent heat of water, how much water is lifted up over a year, averaged over the whole globe, and it's about 1 meter. So averaged over the whole globe, something like 1 meter of water falls. You can do a little bit better than that, because you can also ask how much water the troposphere can hold. And the lower part of the troposphere, averaged over the globe, think of Tel Aviv, is something like 15 centimeters of water at saturation. And therefore, if you have 1 meter of water, and you can't hold more than 15, or in some cases, double that of water, you can see that you're going to have some rains once a month or something like that. So that's the first thing from water. I have a weatherman here from the Army. I don't know if they taught you this way. Oh yeah, I'll be done. There's no problem. I'm stretching it out as it is. Okay, and then you can ask, what determines the maximum size of raindrops? And for that, you have to know a little bit about surface tension. So I go back here. Surface tension occurs because molecules at the surface are missing neighbors. And water molecules like neighbors. And so there's an energy cost to make surface. And of course, that's why small enough drops without a lot of gravity are spherical, as shown in this nice picture here. So it's surface tension that holds the drops together. Now, when the drops fall, they almost immediately they only have to fall 1,000 times their diameters, and they reach terminal velocity, in which case the pressure, the ram pressure of the air as they move through it, balances gravity on them. And that causes them to squish, to become somewhat oblate, something like people become as they get older. And that squishing increases the area. And if the area increases too much, then the cost of all that area is greater than you would get if the drop bifurcated into two, made smaller drops. And that's what determines the size of, the maximum size of raindrops. Now you can very easily show that the maximum size of raindrops then is given by the surface tension, which is about 60 ergs per centimeter squared, divided by the surface gravity on the Earth times the density of water to the 1/2. And this gives something of a few millimeters for the size of the biggest raindrops. And then you can work out for that size using this drag coefficient for a drop falling through air, how fast these drops fall. And you see they fall at sort of walking speed, meters per second. And as Ari told me when we were in the Golan yesterday doing tourism, did he tell students they should just imagine walking with an umbrella and seeing the raindrops come, and you hold the umbrella in front of you. That's if there's no wind. If there's wind, the umbrellas, at least that I'm familiar with, never work. So, okay. Anyway, that's weather. Okay, now I want to tell you one last thing. This is what I told these donors at the Institute for Advanced Study. I asked them. I said to them, imagine that you took off all your clothes. Most of them couldn't imagine that, at least not in public. Imagine you took off all your clothes and you stood out there. How much energy would you lose? Well, most of you probably have almost done that, living in this type of climate. And it's usually not too uncomfortable, especially not during the warmer parts of the year. But you might ask, how much are you radiating? And if you calculate that using the Stefan-Boltzmann law and the T to the fourth, you'll find out you're radiating a hell of a lot more than this 100 watts. But you don't get very hungry when you stand out there. You know, maybe get a little hungry if you go into the water and paddle around a bit. But so the question is, why? How can you sustain that sort of radiation? Does any undergraduate know the answer? There you are, you imagine you're with your friends at the beach wearing a bikini or a monokini or something or nothing. And it's not uncomfortable. Why? If you're radiating all this energy, why isn't it uncomfortable? Well, the reason is that the atmosphere is radiating most of it back. In the thermal infrared, which is what you're radiating, 10 micron radiation, which you're putting out, the atmosphere is opaque. Even in dry days in the desert, it's opaque. And so it's radiating back at you, and the only energy you're losing in net is the difference between what you're radiating out and what's coming back. And that's smaller than the amount you're radiating by 4 times the difference in temperature between you and the atmosphere and your temperature divided by your temperature. So it's a small amount. Okay, so then I actually asked them a little bit different. I said, if you took off your clothes on the moon, how would you feel? And there you would really feel cold. Even if you have an oxygen mask, it wouldn't last long at all. Okay, so this is, and one of the guys in the audience had actually been, not to the moon, but at least up into the space shuttle twice. He had plenty of money. Okay, so that's more or less it. I hope I've convinced you that as you go around and you look at things, physics is everywhere, and you should try to use it. It makes it much more real. Okay, thank you for your attention. Okay.
Questions, please? Yes.
Okay. What makes the food tasty upon cooking it?
Well, that just makes it tasty for you. Now. Plenty of raw meat is tasty to other people even, and certainly to your dogs or cats or so I think that's a lot of that is something that culturally, one of the things that makes it tasty is fat, unfortunately, especially cooked fat. The other thing is sugar, all the things that aren't particularly healthful. And some of those make it tasty to animals too. You can get a dog to eat things that aren't very good for it, that aren't part of its natural diet. But other than that, I don't know. I mean, taste is mainly smell. It's connected with smell. And, but I think a lot of people are quite happy eating raw meat, raw fish, right? So I think cooking, improving the taste is a matter of personal preference, not some very inherent thing. Oh, I actually don't know. Yeah, what is the efficiency of digestion? I guess the answer is what fraction of the calories do you actually use? Unfortunately, for most of us, almost all of them. In other words, what comes out has been pretty well drained. Unfortunately, yeah. Someday we'll be able to eat much more. Because what we'll eat will be, I mean, there are already sugar type substitutes that are like that. You get the taste, but you don't get the calories. But otherwise, I think we're quite efficient. Well, we know the answer, but we don't know exactly. It's hard to analyze. The upper limit for speed of running is only a shade more than 10 meters per second. I think people, on average, the best runners slow down by the end of a 100-meter race. So they're fastest in the middle, and maybe they're a little, but you know, they're slow at the beginning, slower at the end, and fastest in the middle. But it's a little bit better than, maybe it's 11 meters per second. But not much more. But we're terrible. Our muscles are much weaker than those of almost all other animals. Why we develop that way, I don't know. But for example, compared to a chimpanzee of the same weight, we wouldn't have a chance. They're just much, much stronger. Their muscles are stronger.
What sets the speed of thought, human thinking?
Oh, that's a good question. This is a question, what sets the speed of human thought? My son, my younger son, is a neurobiologist. And that's fairly complicated, but it depends what you mean by thought. I mean, so I can give you, I've done experiments on this with him, and also in classes. So here's an experiment you can do in a physics class. You get a group of students, maybe 20 students. You sit them around in a circle, and you have each one touch the shoulder of the one to the right, and be touched and touch to the left, the foot, or you can do it the other way around. So you have a neural path from the foot to close to the head through each body. And then you give them some practice. You say, go, and as soon as the person feels the touch on the foot, they touch the shoulder of the person on the right. And then when the first person started feels the touch from the left, then you click your stopwatch. So you can, this way, you can calculate the time for some impulse to go along the motor neurons from the foot through the brain, and then out the shoulder to the next person. Okay, then you can do the same experiment again, where it's more symmetric. You touch on one shoulder and then the other shoulder. So now you cut out the whole leg. And you practice it a few times. It takes only a few times. Especially with young people, they learn quickly. And you do this, and then you get the difference in those 2 times. Okay, now what do you get from this? First, you can subtract the shorter time, it's always shorter, from the touches just on the shoulders, and that gives you the time it takes the motor neurons from the foot to the shoulder, more or less, to communicate touch. somatosensory touch. And you find, I don't know, you'll find 20, 30, depending on how well they do, meters per second for that. Just adding up all those lengths. Okay, but then there's still time left over. And that's telling, having the impulse come in this way, get processed through the brain, and come out the other way. And that's non-negligible. So that, in some sense, is how long you take to process and push out that information. And that's slower. Those are slower, but there's shorter distance, because your brain is fairly compact. And there the electrical impulses are going through much narrower wires. They're still myelinated. So they still have insulin around them. And so it's slower, but I don't remember exactly how much, and also it's a very crude thing. But it's a very nice experiment to do, and it's very reproducible once you have a group that has practiced a bit. Yeah, so that's a nice one. Unfortunately, humans are lacking the ability to use inductance. So our neural functioning is really like the old cables that were laid across the Atlantic in the 1870s. They work just with resistance and capacitance and diffusion of charge and repeaters. But we haven't been able to develop anything like inductance. So we don't have fast, we're slow, we're very, very slow. Someday we'll be engineered better, but then we won't be us. We'll be something else. Soon. Okay.